Okay. Hello, everybody. Good afternoon. Thank you for coming. Appreciate you coming to this session. My name is Christian Schmutzer, and I'm happy that you're here. Maybe a few words about myself. So I joined Cisco in 1998. Yes, I was a young boy back then. Since then, I grew gray hair, a little bit of a belly. But you know, that's what's happened when you get older. Over time, I had the luxury to learn a lot at Cisco. Actually, when I joined, I think it was perfect timing because ATM and frame relay was still a thing. When I talk to young colleagues joining the company now, they mostly like shake their head and they don't know what I'm talking about. And actually, MPLS was still called tag switching. Some of you, still somebody remembering tag switching? There you go. Yeah, welcome to the gray hair club. We all went through the same. I think the most exciting thing about this over 25 years now is that early on, because I came from my studies directly to Cisco, and in my studies I worked on optical technologies. And around 2000, Cisco started acquiring a bunch of companies. Pirelli Communication Networks. Yes, everybody wanted to have a calendar, right? You remember that one? We bought Serent. We brought a bunch of other companies, I think Pipelinks and whatnot. It was really an exciting time, and I totally jumped onto that. And doing so, I had the luxury to actually now slowly build up knowledge in both the IP and the optical world. And I have to say that is the best thing that happened to me professionally, because I think this is a great place to be, because combining those two worlds is not that easy. And if you can do that to a large extent, I think it makes you actually, it's kind of like a job protection, and it also is a lot of fun. What I also did is, to a large extent, something that not a lot of people do. I started as a system engineer in the small little country Austria. Here it's not too far away. When I speak in Melbourne or in the US, it's a little further away. I started in sales, went into marketing as a TME for the Frankenstein router, Cisco 7600. Somebody remembers? Yeah, I see some people laughing, yeah. Some people called it Catalyst 6500. And then over time, I became, I basically continued my journey and more got closer to engineering. And now I have the fun job of thinking about problems. And most of the time, I have also the luxury to select the problems I want to solve. And one problem that I selected is private lines, and this is what I want to talk to you about. And if you wonder why is the picture up here, if I'm not thinking about private lines and technology, I like to ride my motorcycle on the beautiful roads of Sardinia. I think you have seen this slide. There is a WebEx room. You can ask any questions. I will monitor that. But I will be here until tomorrow evening. So if you want to talk to me, please feel free to join, to reach out to me. Okay. So let's start with this one. And I let that sink for a second. And you were probably wondering what the hell is this slide about. But I have been talking and working on emulation and TDM technologies for quite a long time. I've actually renewed the emulation implementation of Cisco for PDH and Sonnet SDH roughly around 2015. And now, I'm going to the bigger speeds. And over time, I started to think, this is all cool, optical networking, all the requirements, and how is IP different? And then I said to myself, why are those two worlds not understanding each other sometimes? And why is it so difficult? And I think what some people may have forgotten, some of the things that we want are really rooted in the past, where Alexander Graham Bell invented the phone. You could pick up the phone and had a voice communication. And for that communication to happen, you had basically to have a cable, right? First it was analog, it became digitized, right? We started multiplexing 64 kilobits into 2 megabits, we multiplexed it into E3s with PDH, into STM1s, STM4s, STM16s, using SDH. Yes, a Cisco employee can actually spell SDH, not Sonnet. So that happens. At some point, SDH was not fast enough. We went into OTN, the optical transport network, which was initially a framing technology, then became a multiplexing and switching technology. Of course, then we also had wave division multiplexing. Essentially what we did is we tried to increase the capacity and the reach of our network so that we can build voice networks that span the globe, right? Now, how many actual voice systems do we still have out there? I would say not that many, right? I mean, early days we had this famous chart where voice traffic was growing, and then you had data traffic, and essentially we always showed kind of like how actually data traffic surpasses voice traffic, right? I mean, it's not really about carrying voice that much anymore. But if you think about it, transport networks are still built with this Russian dolls model, right? We're having a fiber, we have wavelength channels in the fiber, we have TDM time slots, so on and so forth, and the slots are on different sizes. Now, why do we have that? Well, it's not all bad, right? Having this onion model is actually quite beneficial, right? Because obviously, putting fiber in the ground is expensive and labor, exhausting, right? So if you put the fiber in there, you want to get the most money out of it, right? So if somebody wants a fiber, right, you probably as a provider would not say, hey, sure, no problem, I have 500 strands of pairs of fiber, just take them, give me $5,000 a month and I'm fine, right? No, you don't want to give it because it's the most expensive asset you have. So being able to multiplex multiple services with wave division multiplexing or time slot multiplexing obviously is very convenient. You can separate different customers, but you can actually have them on the same infrastructure and you're not giving them your precious asset. So essentially what we do with private lines, or what are people doing with private lines they get from providers. Typically you build some kind of network topology, right? And for the most part, by the way, can we do a show of hands who would call themselves a provider and potentially having fiber? Okay. Who would say is more of an enterprise customer or some customer that requires connectivity? Okay, cool. I think there are a few people that haven't decided yet, but that's good. So I think it's, I would say, two-thirds provider and one-third enterprise. So we have providers providing those point-to-point connections to enterprises, for example, to interconnect the routers. And obviously, if you interconnect the router and you're actually building your own network cloud, if you will, the cables, the virtual cables you use to interconnect your routers, you want to really know what they do, right? How much capacity do they have? Are they up or down, right? They should be as close as possible to a cable, but you have to rely on somebody else to implement that virtual cable, if you will. Then we have people that have, obviously, redundant data centers, right? So you have storage area networks where you have potentially synchronous replication between two data centers roughly 10, 50, 60 kilometers apart, and you interconnect fiber channels, right? And if you want to interconnect those fiber channels, you need highly reliable connectivity, often done by managed wave division multiplexing. And last but not least, by the way, I promise there is no single mentioning of AI in my presentation, right? Thank you. But I mentioned cloud, okay? I mean, I can't do everything, right? So I can't do a cloud and AI-free presentation, but at least there is no AI on the slides. But if you want to have connectivity between some resources in your location and in the cloud, Azure, Google, AWS, you probably want to have some reliable high-capacity connection, right? Now, what I actually haven't done, even though I'm constantly updating it, there's even a fourth, thing, and I mention it because now it's like, everybody talks about it. These, satellite networks that are appearing are one thing that I see that actually is also a driver for private lines, because now those satellite networks on constellations get deployed, but they don't exist only of things that are kind of up in space. they also have base stations that they have connect to, right? And those base stations need to be spread across the globe, and you have to connect them. And of course, these connections have to be reliable and high capacity, and that's where private lines are also commonly used. So what are private lines? And I'm using a very, let's say, abstract definition to kind of level set, because in the end of the day, people call it wavelength service, some people call it, private lines, many different, point-to-point EPLs and whatever, right? But they all have in common that they are fairly high capacity, and that capacity should be as good as possible allocated to a particular customer, right? It's kind of this precious resource, kind of like it belongs to me, nobody else is allowed to steal my bandwidth. But also, I'm paying something for that, so I would appreciate if the bandwidth is really kind of allocated to me. They should always be available, right? A private line is a premium service. It's not like some best effort, Wi-Fi connectivity. It's actually something that you buy and you expect to be there. And then, depending on the situation, yes, most of the traffic is Ethernet and IP, right? I mean, everything spits out Ethernet and IP. Luckily, we don't have ATM to the desktop. We don't have any of those, strange things too much. I know that talking about private lines and emulation, I'm meeting a lot of customers. They come with, oh, I have this signal and that signal, right? So, but the predominant, carry data that needs to be carried is Ethernet. But we have, of course, fiber channel. We have SONET, but we also have some strange video or control signals, of course, as well. So why did we use TDM or wave division multiplexing so far? Well, pretty easy, right? It is giving me the opportunity to have a dedicated wavelength or a dedicated time slot to a particular connection, right? And if I establish the connection, it's allocated and it can't be taken away. The technologies have overhead and OEM capabilities built in. There is nothing that you have to put on top of that. It's just built in natively, and that's what a lot of people like. And TDM and wave division multiplexing systems are generally payload agnostic. You can pretty much take whatever you want and map it into one of those channels. Now, why are we not continuing with this? Well, there are two kind of points I want to bring out here. Time has changed, right? And I mentioned the 7600, right? So back in the days in around 2005, we barely could build a 10 gigabit line card. And believe it or not, the first 20 gigabit line card for the 7600 was nothing else than double the ASICs on the same card. It was like getting denser and denser, and that's it, right? And when we wanted to build a 40 gigabit line card, we were really struggling, right? Nowadays, honestly, we are struggling to build small things, right? The last box that I built or designed is a 1IU box having a bunch of 25 gig and 10 gig ports. I will actually have a slide up about it. There is a 1.2 terabit ASIC in it. It's the A100 Silicon One ASIC, right? Basically, bandwidth in the Ethernet switching and routing world is abundant, right? We have more capacity than we actually can use. On the flip side, technologies that normally, in the past, were more cost efficient and more scalable, like OTN and SONET SDH back in the days, they have been stagnant, right? There is no development going in there. So basically, if you look at the capacity per chip, you see that basically TDM technologies are really kind of like, the OTN technology could go, or was going up until 1 terabit, but there it's done. It's, nothing is gonna happen, right? And actually, I think with the 1 terabit, I'm actually, double counting to the favor of the chip manufacturer, so it's even half of that. And then, thanks to folks like Acacia that joined Cisco, we have made a lot of progress in integrating optics, making them denser and integrating them into pluggables, and now you can actually directly shoot optical signals with a specific wavelength out of any port that you normally would also put a normal SFP in. The second thing that is happening is that optical transport networks are getting out of fashion. And why? Well, if the chipset technology is not improving, overall, the cost per bit of transport of OTN is falling behind IP and Ethernet switching and routing, whatever you want to call it. Then you have a lot of vendors out there that that have various different platforms, and they also have the challenge of renewing and evolving the platforms. But if you don't have new chipsets, I mean, how can you build a new box if you don't have new elements to build the box, right? So there is a little bit of a kind of challenge going out there. And what I'm showing you here is a survey that was done by Heavy Reading together with Infinera. And they asked, I think, 117 customers, what's their plan with OTN, right? And you see that actually 5 to 10 years ago, people thought OTN will solve world hunger. Nowadays, people say, well, I'm not sure, right? Some people are very aggressive, saying, I don't want to deal with this anymore, I rip it out. I would say that's very aggressive. But I think what that shows here, to me, is that it's not that OTN is the most favorite kid on the block. It's actually more on the sideline, and people are really thinking about doing something different. And I would say that led to routed optical networking making sense, right? Why not build a network that uses at the electrical layer a technology that is most scalable, most cost efficient, and requires the least amount of power, and then you put that on top of a optical layer of your choice. It could be very simple, maybe a bit more fancy with ROADMs, but essentially, why not build a very simple integrated IP and optical network? So by the way, did anybody miss the agenda slide? We're not there yet. I'm trying to construct my agenda, and in order to basically make sense of the agenda, I really want to say, well, we have level set now, we want to build a scalable integrated IP network, but this IP network somehow is not satisfying our Russian dolls model, right? We're not really able to create a connection with a bandwidth and a certain path, right? We kind of have this cloud where you can send packets in, and if you're lucky, the packets come out on the other side as you intended. So what we actually need to do is to make this fancy cloud behave like a circuit, right? Make a connectionless IP MPLS segment routing network behave like a connection-oriented TDM or wave division multiplexing network. We want to create a point-to-point circuit. It should be able to carry whatever I want. I want to have some fancy OEM. I want to be able to instruct the network how to establish the path. I want to have the path potentially bidirectional and co-routed, meaning traffic in both in either direction goes along the same set of links. And we talked about bandwidth because people are greedy, right? They want the bandwidth of their circuit belong to them and not be taken away from anybody else. And in order to do that, I have prepared an agenda consisting of 2 points, right? And as you see, I hate text and I like pictures, so my agenda slide looks like this, right? I'm going to cover 2 things. First, we're going to talk about the service layer of our network, and I talk about how we can make pseudo wires which allow us to do a point-to-point connection to become bit transparent and be able to carry any data that you want and also give us some good OEM. And the second part of the presentation will talk about the underlying network transport and how we make that underlying transport to be connection-oriented and end-to-end path protected. Okay, first section, private line emulation. Private line emulation is essentially completing our service portfolio, right? For the most part, if we carry Ethernet, an Ethernet point-to-point layer 2 VPN is good enough, right? But the question is, do we maybe want to do something different? Because some people actually say their Ethernet pseudowires are not transparent enough. Now let's have a look, what does a router do if it receives an Ethernet frame? First of all, an Ethernet frame at the optical fiber really is a sequence of 0 and 1s, right? So let's think about, you have optical light coming in into your port, you have 0s and 1s, and then we move up the IEEE stack, the physical layer, right? So you're gonna make sense of the zeros and ones, you're gonna see that there is a 66-bit code stream, then you're gonna start trying to find out their frames, there is a destination, a source MAC address, an FCS, and blah, 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 and at some point, you're gonna see a VLAN, and then you take that packet, store it, make a routing or a switching lookup, and process the packet. In order to be fully transparent and to implement what we call private line emulation, we are basically changing this massively. Ethernet is still zeros and ones coming in. But what we have defined is, at the 66-bit PCS layer in the PHY layer of the IEEE stack, we're gonna stop processing, right? And what that makes us is essentially be agnostic to any notion of a frame, because all we know is 66-bit code words that are sent, one after the other, and that's it. And this gives us transparency. We do that for Ethernet, but also we do that for fiber channel, SONET SDH, OTN frames, whatnot, right? We're taking the bits coming in, put them into packets, put some header on the packet, and send it across a pseudowire, which is the logical entity that represents a point-to-point connection. Now, I can proudly say that the idea came with a colleague of mine, Luca, and with some customers that actually said, hey, can't we do something different? And we started kind of inventing this, right? But really, it is nothing rocket science. What we really did is we used some already existing TDM emulation concepts that were defined by the IETF in RFC 4553, but were really specifically specified for carrying E1s and T1s, E3s and T3s, so basically PDH type stuff. And we took these concepts, refined them, and focused some of the functions onto carrying high-speed signals, but essentially doing more or less the same thing. And we have published this via the IETF. Now, what can we do with it, right? We can carry STM16, STM64. We are treating these SDH interfaces as big pipes. We're not looking at the structure, right? Remember, I talked about bits coming in. We're not really trying to make sense of the structure. We take the bits and put them into packets. So we don't know how much channels do we have in that STM16. We know that there is an STM16 port, and we just want to carry the data. We can carry OTN, Ethernet, and fiber channel. Everything that you see in the table is specified in the private line emulation draft. Everything you see green circled is what we ship today in a particular product that I will show you in a second. So I'm very happy to announce that I was really lucky, because when was the email? December 19th. So basically, that was probably my professional biggest Christmas present I could have gotten. The draft got approved by the IETF board to be a proposed standard. Essentially, private line emulation as of end of December is a standard, approved by IETF. What's still missing is the number. Let's see. I'm not sure if that actually may be one of the first 5-digit numbers, because I think we're in the 9,000 somethings. But essentially, I'm really happy. It took a couple of years. It's my first, rodeo. I have never done this. I was a consumer at IETF. This is the first thing where I have been an editor and driving something. So I'm very happy to see that. And it actually is a testament of everybody that was involved. We had multiple vendors being involved, multiple customers, and really this is something that shows that this is not a specific Cisco technology, but actually something the market is interested in. Now, I think one key point to make something like this successful is you have to think about what are people doing today, and how would you do that in the future. And we took a lot of time thinking about how does an OTN network operate today, and we want to make sure that every single mandatory feature that people are using is also possible in private line emulation solutions. And the first thing that we want to worry about is actually failure indication. right? So for example, if a customer port would go down, somehow the other side should be notified, right? Because I mean, the loss of signal on the left side doesn't just magically get communicated to the right side. You need to do something in the network. And OTN does that by using a specific overhead signal called CSF, client signal failure, right? So if the port goes down, the remote end will receive that and instruct the remote OTN switch to say, hey, indicate to the client that actually on the ingress of the network we had a problem. And typically a local fault signal for Ethernet would be done, an AIS signal for a TDM signal, or in a DWDM system with an old transponder, optionally sometimes they just turn off the laser. So how do we do this? We're actually using some pseudo-wire overhead, right? And the pseudo-wire overhead that we're using here is called the control word. And in that control word, we have a bunch of things like sequence numbers to detect loss, but also we have two bits, the L and the R bit, okay? And in order to show that, people say 3 times is a charm. I have been demonstrating something for the whole week. By the way, who was there on Sunday in the tectorial? Okay, no, there are 1 or 2 people are here. And who was in the presentation yesterday? There you go. Wish me luck. So this is a little bit redundant for the people that have seen this yesterday. But I thought, it was working so great, so why not do it again? Okay. So in order to show this in action, I think is much nicer. So we have our network. Left and the right side is the endpoint of a circuit. And I have an OTN tester connected to. I have prepared a small little Grafana dashboard. And that Grafana dashboard shows us basically what's the state of the port on the left side and on the right side. You see receive and transmit power on the client. You see OTN-specific alarms, because I'm actually having here an OTN-emulated circuit. And what I'm showing you in the diagrams here is actually whether we receive or generate L and R bits, okay? Now, we were talking about a failure on the client. So this is the OTN tester, right? Think about this is the device that the customer would normally connect to the service. And let's just say there's a fiber problem. I'm turning off the laser. That means that the service provider's equipment doesn't receive any light. So what should happen, right? We talked about the L bit. We didn't really talk about it, I just mentioned it, but basically what the OTN network does with the client signal failure overhead, the pseudo-wire network does with the L bit, right? It's the local failure, if you will. So what you see here in the Grafana dashboard, the optical controller detects loss of signal. It says, I don't see light. You see minus 40 dBm. The OTN controller is detecting loss of frame. Now you would wonder, didn't Christian say we are bit transparent and agnostic to frames? Yes, we are from the data plane perspective. But performance monitoring-wise, we are able to do non-intrusive performance monitoring. So we actually know what the structure is, and we can tell you what's going on. But this is only for monitoring. We're not interfering with the frames. But because we had a loss of signal, you see that the left side generated pseudo-wire packets with the L bit set. The other side was receiving them. And as a consequence, the other side, of course, acted upon and triggered an AIS, which the tester is now receiving. And essentially, this is nothing else than a live demo of the slide I showed you before. We also have another bit, and the second bit is called the R bit. What is the R bit used for? Well, we want to distinguish a client failure from a network failure. And there's one particular network failure where, for example, a endpoint does no longer receive traffic because there's a unidirectional problem in your network. And I want to introduce that by essentially dropping traffic in the node Ravello, which basically makes Palinuro, the node on the left side, no longer receive traffic, though the traffic towards the other direction is still going fine. So, in order to demonstrate this, so you see we cleared everything. Now the L bit is no longer being sent and received. Let's go to this Ravello node. What I did here in this lab is I artificially marked my PLE traffic to EXP7, right? Not really a realistic example, but by doing so, I can put a policer matching on that EXP field and dropping traffic. So what you see is, first of all, let's go here. Obviously, I should have cleared this. What is happening is, okay, this is the grumpy Viavi, not having enough memory. But what you see is essentially, if the left router doesn't receive traffic, I'm dropping half of the data plane traffic. Obviously, we take, in order to play out bits, we have to replace them, and we are using replacement traffic. But that traffic is just a fixed pattern, and that leads to frame errors on the tester you see, right? Essentially, when you drop traffic, you will see that it's kind of similar to you would have bit errors on an optical communication. What's also happening, and we need to scroll down here, we mentioned the R bit. The left side doesn't receive packets. It goes into what we call the packet loss of signal state. And we're doing a backward defect indication, a BDI type of notification that OTN would do as well. And we do that by sending packets with the R bit, and again, the other side receives that. So in essence, we have two bits. They mean different things, and it's very important. You lose something, and something happens on the client, but you want to make sure that you can distinguish between, is there something going in the network, or is there something going on the customer side. With this, let's go back. This one, I guess. Okay. And for the ones that were yesterday, I slowly learn what button to push. I'm not there yet. But okay, we talked about this, blah, blah, blah. There you go. Okay. In order to do all of this, there's also one fundamental requirement I wanted to specifically mention to you, and this is the two endpoints have to have a common clock reference, right? Because when we send bits across, right, we are acting completely transparent, but we are not having a TDM switch network in between, right? So somehow we need to deal with the fact that we receive packets, and we somewhat need to understand what was the frequency of the bits coming in on the left side and regenerate them on the right side. And the foundation for doing so is to have the two nodes being synchronized and locked to the same clock, right? It can either be via an external timing input. You could use frequency, physical frequency synchronization using SynGi, and you can use PTP. Any of those choices is fine with me. So how do we actually represent, the frequency of the bits coming in here so that we can have that on the other side? And the way we do this is actually we are using a concept called differential clock recovery. And in order to do that, we need to put timestamps on the packets as we put them into the pseudo wire. And essentially what the timestamp is saying, you have a common clock. The clock is ticking, 1, 2, 3, 4, 5, 6, 7. And once you're done receiving all the packets, you basically have a count of like 754, and then you stamp that packet with 754, right? And that 754 is a representation of the time and how many clock ticks it has taken to receive, let's say, 1,000 bits. On the other side, we receive the packet stored in some digital buffer, and we're looking at the timestamp and compare that to the same clock. And as the same clock on the other side is basically having the same tick, right? We know what 754 means, and basically by putting the differential, we can create a clock at a certain speed and play out the information that we have received from the packets, right? So essentially on the ingress, we do timestamping in reference to a common clock. On the egress, we take the timestamp, compare them to a reference clock, and we send out the bits with the recovered clock. I mentioned the digital buffer, right? And maybe let me spend a second on what that digital buffer is used for, and also let me talk about something that often comes up, private line emulation or packet networks and delay, right? delay is not introduced by routers, right? Nowadays, a router takes roughly 3 to 5 microseconds to switch a packet from the ingress to the egress, right? So they're really, really fast. Actually, the transit latency through a router is potentially 1 order smaller than of an OTN switch. I have measured OTN switches to show roughly 30 to 40 microseconds. I'm not trying to make a speed competition between OTN switches and routers, but I think what I was trying to say is the delay through a router is in the microseconds, and it's not in the milliseconds. However, being a connectionless packet-based network, you have to deal with packet delay variation, because obviously, only one packet at a time can be sent out on the wire. So if you have to wait behind another packet, those packets that come in from the left to the right, they will not always be received at the constant rate. So you have to deal with that, and that's what the digital buffer is for. We're going to fill the buffer to half of the level. So if we don't receive enough packets, we start depleting the buffer. And if we receive too many, we start filling up the buffer, right? But with using that digital buffer, we still always have enough information to play out bits, right? And also we don't hopefully have too much information to let the buffer overflow. A buffer can be implemented in the size of roughly 300 to 400 microseconds using internal memory of an FPGA that's in the PLE platform implementation. Using internal memory is making it cost efficient, and 400 microseconds actually is way enough to, for example, have a circuit span roughly up to 30 hops, which obviously I think is quite a bit of a distance. I'm not going through that. There's a bunch of configuration examples. I just put that in here for reference. And this completes the first section. Essentially, we made our network be able to create a point-to-point circuit. It is bit transparent, and it gives us OEM. Okay. I need to speed up a bit. Circuit-style segment routing is the tool in a segment-routed network to achieve what we want to do from a network transport perspective. And what in a TDM world for private lines we generally want is the ability to steer traffic along a deterministic path, right? We want to have bandwidth or resources allocated along the path. And we don't only want to have one, but we actually want to have two, a working and a protect, right? And whenever the working is having a failure, I'm going to want to switch to the protect. And when the working comes back, I'm probably going to go back to the working as desired by my revertive policy. Now, how can we give you that behavior in a segment routing network was the question, and circuit-style segment routing is the answer. Essentially, it gives you the ability to do bidirectional, co-routed, persistent paths. With a path computation element, we add the notion of bandwidth management. Using active probing, we can do path OEM, so we can actually detect within 10 milliseconds if, for example, the working path is down. And by establishing pre-programmed backup paths, we can do end-to-end path protection. Now, the key element of circuit-style segment routing is what we call the adjacency SID, right? The adjacency SID is nothing else than a segment ID that represents a particular link in a topology from the perspective of the router connected to it, right? So, for example, 15.0A1 from the context of router A means the link towards 1, and 15.012 is the link from 1 to 2, right? This can be an MPLS label. This could also be an SRv6 microSID. It doesn't matter. Let me just call them segments, and bear with me if I mostly talk labels, but I think it's just simpler from a talking perspective. So segment routing is a source routing principle, right? So I can put a list of those segments on a packet, and essentially, as this packet is being received by a router, it looks at the label or the segment and say, oh, looks like this is the segment that belongs to that link, and the router sends the packet over here. As the router comes in here, we're looking at the segment and say, okay, looks like I have to go here. And whenever a router receives a packet with an adjacency SID, It does the lookup, removes the segment so that the next router is essentially seeing the next adjacency SID. And with this, you basically on a hop-by-hop basis can determine how the packet should go through the network. The same principle we're also using for the active probing mechanism, or SRPM, but we actually do something very clever on top of that. We are not only encoding the forward path, but we're actually also adding the adjacency SIDs for the reverse path, which means if you generate a probe with these 6 adjacency SIDs, you're sending the probe from here to here, from here to here, from here to here. Then this guy is seeing actually segment 2, the adjacency segment 2, which is the adjacency SID going back, and then essentially your probe is getting looped back to where it came from. And with that, each of the endpoints can do active probing and on its own detect if there is a failure. Now there's a very nice side effect of that, right? Due to that loopback nature of the probing, both endpoints can detect unidirectional as well as bidirectional failures, and they switch over at the same time. There is no protocol like an APS protocol needed to control the switches on both sides. Speaking about switches, circuit-style segment routing is using SR policies. SR policies are logical constructs that you want to call tunnel as well as if you want. Generally, an SR policy only has one active candidate path. Essentially, you may have configured multiple of those, but it always picks the most preferred and available one. In this case, we want to do this a little different. We want to have one candidate path that is the working and another one that's the protect, and both of them we want to have programmed in the data plane. Having said that, only the working is carrying traffic and the protect is only carrying traffic if the working goes down. From a semantic standpoint, we have an SR policy in one direction and an SR policy in the other direction, each on the corresponding endpoints. In order to facilitate centralized path computation, we need to associate the two unidirectional entities to form a bidirectional construct, and that's what's called the bidirectional association. And that's basically an AID that we allocate. So why do we actually care about end-to-end protection? And let me maybe remind you, we have MPLS TE FRR for a long time, and we have loop-free alternate in segment routing. Those are local protection mechanisms. They're super great, right? Many, many different flows and routing entries can be switched over in one single shot by detecting a local failure, right? So why do you not want to use them for delivering private lines? Well, there's one simple answer. For private lines, we want to have bandwidth guarantees on both the working and the protect in all the cases, right? And the problem with local protection is you're actually sending traffic on some detour away from the failure. And it's very hard or impossible to precisely expect the utilization in those kind of failures. You can do what-if analysis, right? But a priori, when you provision something, you cannot predict every single failure and every single case and what the utilization will be. If you do end-to-end path protection, you can do bandwidth accounting for the working, bandwidth accounting for the protect, a priori when you provision. As during the protection, you switch the traffic from the working to the protect and only to the protect. You switch the traffic only where you planned for traffic to be flowing. With this, you can, ahead of time, make all your bandwidth accounting and make sure that you have never any congestion. Again, reference slide, I want to go through that. Reference slide on. Now, I talked about this list of segments, right? You can do those manually, but I guess if you want to do that for 5 to 6, 7 hops and for many, many policies, you're probably going to start saying, well, Christian, this is not so much fun. I may have use cases where I explicitly want to define them, but really in most cases, I want to say, I go from here to here, I need 11 gig, please tell me what to do. And the path computation element is the centralized entity that can do that. In the circuit-style segment routing solution, we have defined that the endpoints configured for policies can use the PSEP protocol to go to the PC and say, hey, I want the working and the protect path. I don't know how to route it. Can you please help me? And the PC will basically get the request. It knows the topology. It knows all the policies that have been requested and provisioned. It will find a path, send a response. There you go. The policy gets established. Now, talking about path computation and the persistency, I also wanted to point out one thing. And I learned that the hard way. Before I have been working with the team on circuit cell segment routing, I worked on something what we call at Cisco Flex LSP, or co-routed bidirectional traffic engineering. And we have done this in phases, but when I looked at the solution and proposed it to a big service provider in the US, we quickly realized, yes, you can do co-routed bidirectional traffic engineering, but the implementation wasn't really doing what the customer expected. Because what the customer expects actually in a private line environment, if you set up a working path, the working path never changes, right? You switch to the protect, fine. If you add a new link between A and Z, even if it's the shortest path, right, you should not use it, right? Yes, if the operator is saying, I have added my network, it's more optimal now, can you please re-optimize on request? Yes, the working can change. But it should never change just without the operator's acknowledgement. For this, you need to make the LSP or the path persistent, right? And this is the key functionality we have implemented in our path computation implementation to say, we compute the path, and once we compute it, we're never gonna recompute it, even though the network changed and there could be another option for routing that working. Okay, when we route the paths, obviously, how do we ensure, I can say, hey, I think I have bandwidth there, but how do we really ensure that the bandwidth that I have allocated is actually really given to the particular customer? And we had a lot of debate on this, and I think this is also something where you really have to think a little different, right? If you give a time slot to somebody, the time slot belongs to that circuit and it's gone, right? In a connectionless network, you can't really do this, right? We're using statistical multiplexing, packets are shoved into an interface, into the queues, and that's it, right? But it's actually very simple, right? If you don't commit something to somebody that you don't have, then you're staying out of trouble, right? So basically only commit what you have, right? Meaning never overutilize your interface. And as long as you distinguish between things that, traffic that is belonging to a commitment and traffic that doesn't belong to a commitment, you can do something very simple. All my commitments, I can either assign the whole interface or just some portion of my interface. All my commitments are being tracked. And if my pool is full, I'm going to move on and route my traffic to some other interfaces. I'm no longer put some commitments onto that interface. And if I do that, I will never lose a commitment because anything else that didn't get a commitment will be in a lower priority queue. And if the interface is congested, traffic gets dropped. But who is getting dropped? Only the traffic that belongs to a non-commitment, right? I think this takes a little, to think through, and I think there are a bunch of concerns that I always see. But for me, honestly, it's a very simple solution. And in the end of the day, I no longer need to slice and dice my interfaces. I don't need to manage time slots. Some people say, well, why can't you do like VLAN allocation, whatnot? But why? If you follow those very simple principles, that you only commit what you have and make sure that commitments are higher priority than non-commitments, you will always have a solution. Yes?
Is it really the highest value? Because I want my network management traffic still.
Very good question. The question was, is it really the highest priority? And the answer is no. And you see that's what I'm trying to show here with network control or whatever it is, right? Obviously, in the description, I tried to simplify, but essentially the important part is commitments have to be higher than anything else that might be of high bandwidth and has no commitment, right? And luckily, network management, control, whatever, is going to be fairly confined in the bandwidth, and you basically would treat it as higher priority. Thank you very much. Good point. Now, this one is a fun one. When we made traffic engineering more private line-ish, right? Meaning we have persistent paths that don't change, right? There is actually something very interesting that is happening as well. If, for example, you have a failure, normally traffic engineering would re-optimize and would re-establish a working path. So even though you have to protect after, you switch to the protect, but after some time you re-establish the working, you may switch back, right? And with this, you're again in a protected state. In a TDM world, if the protect goes down, it stays down. You're not re-optimizing, right? Meaning, up until this path is actually restored, you are in an unprotected state. All you have is your protect. So far, you probably say, well, why is this a problem? Well, one failure comes never alone, right? There's often a second failure, right? There's maybe a third failure or a fifth failure, depending on where you are. There can be many failures. Now, if you have actually a failure that addresses, impacts the working, and there's another failure that impacts the protect, per definition, both paths are persistent, they should not get rerouted, and you would stay down. Your service is completely down, right? Even though you have actually a path that goes like this, right? Why not use that? And that's where actually in the TDM world, people talk about 1 + 1 + R, or this notion of restoration is coming into the picture, right? So you have protection, where you have two things that protect each other, and you have pre-allocated resources. You can switch within 50 milliseconds. But then there's also restoration that you generally do on demand. So if something catastrophic happens, you're going to try to say, hey, is there something that I can do to bring my service up? It's not a path that I would love to have all the time, but wouldn't it be great for that portion until I can start repairing my network to bring back the service and the customer? And that's actually what we can do in segment routing as well, with putting a third candidate path. That third candidate path will not be active per default if both the working and the protect are up, or actually, sorry, not both, but as long as one of them is up, that third one has nothing to do, right? But as soon as both of them are up, as both of them are down, we just say, hey, it looks like we have a problem. Let's ask the PCE, hey, is there another path? And essentially, we do an on-demand path request and figure out, is there a path that satisfies the bandwidth through the network, and can we bring up the service through the network until the working or the protect comes back up? Because we kind of have this dynamic on-demand nature in IP and segment routing, this was very easy to do. Doing this in a TDM world is not that easy, even though you have implementations, but I think this was something that I wanted to point out, which really is in the DNA of a dynamic network. Some configuration. I don't want to bore you with that. Same story here. We are a little behind. Not really behind. I guess PLE was faster than circuit style. But again, we are in what we call the state of workgroup last call. So we're kind of in the finishing, on the finishing line of standardization. Now, when I say standardization, circuit style segment routing isn't really something new. It's kind of a solution description of existing, already standardized segment routing components. So this will actually become an informational draft or informational document from the ITF. So it doesn't specify a new standard behavior, but it's kind of a agreed upon solution description, if you will. And hopefully this will become ratified as well soon and get a number as well in the next couple of months. Okay. Back to the agenda, right? Now we made our network be able to route bidirectional co-routed. We established protected paths, and we can manage bandwidth. So we're also at the finishing line here. So let me close with a few words on where we're at and where we go. So the PLE journey started, I don't remember exactly, but probably like, things always take time. I think 2018 or 19, I was starting to discuss this with executives in the company to say, hey guys, you know, we need to do this. Took a little while, as usual, but in summer 2022, we had our first implementation, right? And how you get something done in a big company, you use an existing router, like the 55A2 and the 57C3, and you add what is missing. And what was missing was an FPGA that can take bits and create packets. And then we put that FPGA on a card, put the card on a router, and then the router does forward the packets, right? Essentially, the easiest way to get going. With this implementation here, you see the card. We have 8 ports. You can configure any mix and match of those, GIGI, 10 gig, STM16, STM64, fiber channels of various types, and OTN. Now, the first deployments we have had, funny enough, when we defined the capabilities, I wasn't really a big fan of supporting fiber channel. Because fiber channel is, for me, a storage area interconnect solution that normally is between 2 close-by data centers, and that's normally a dedicated DWDM system that is being used. And we're not gonna really hit the price point, but what actually has been interesting to see is that those managed services are, for quite a few customers, somewhat painful. They don't want to deal with that. And I have one customer that said, well, I have this big segment routing network with a lot of capacity. I just put your PLE nodes onto the network, and I carry a bunch of 8 or 16 gig or 32 gig fiber channel across. They are like white noise behind all the rest. And I don't have to deal with a dedicated managed DWDM network. Question?
Distance limits?
So the question was, do we have distance limits?
Yes.
Yeah. The technology in itself does not have any distance limits. I mean, honestly, we could do private line emulation across the globe, right? Of course, the longer the distance, the longer it takes for the information to flow from one end to the other, right? And that's where fiber channel and the buffer-to-buffer credit mechanisms of the fiber channel come into the picture. And that's generally why people, when they do direct fiber channel SAN interconnects, they're very close by, because for synchronous replication, the longer the further you're away, the slower and the lesser the performance you have from fiber channel and synchronous. So it stays everything the same. Compare it, your distance and design assumptions will be the same as you would use DWDM or private line emulation. The only difference is private line emulation can be run over routers, and DWDM you have to have fibers. The path computation element is also implemented first in CNC, or the Cisco Network Controller version 5. We are now, I think, at the version 7, so we have also made some more improvements. So essentially, what I'm trying to say here, all you have seen here is not wishful thinking and PowerPoint, but it's actually reality, and we have shipping products. What we don't have yet, but what we're actually doing to evolve the solution. Oh, question. Very good question. Is this solution supported with SRv6 or only MPLS? The answer is today only with MPLS. We have many customers asking for SRv6. So as we progress through the roadmap, I would expect SRv6 support to be added in the next 1.5 years, hopefully. So the standard is defined already for SRv6. So if you look at the document, we have all the behaviors and everything defined. From an implementation standpoint, I have the design how we do it. So I have figured out everything with engineering. We just need to formally productize it, and hopefully that will happen in the next 12 to 18 months.
So CNC side.
Exactly, yeah. That all has to come together, yes, yes. Is there, okay. So what we are trying to do here is, the boxes that I showed you before are great, but they're fairly large, right? If you want to put something at a customer premise, you may want to have a more optimized device. So what we're looking at, actually building a set of devices, and this will be the first one, to have 2 ports of PLE of 10 gig and a bunch of 25 and 50 gig Ethernet uplinks And you can take that and, for example, put it at the customer premise and have a so-called CPE, right? Or a demarcation device that you can actively manage and establish the connection. Of course, you can also put them in the location, in your POP or central office, and dual home them, for example, to any of your existing routers. Obviously, this may not be super efficient if you have like hundreds of those, right? But the beauty of this solution is it's kind of a pay-as-you-grow approach, and it allows you to provide the service independent of the nature of those two routers. They can be Cisco routers, they can be other routers, so basically we're decoupling the PLE capability from the network, and that helps with the adoption, hopefully. Yeah.
In case I use
I repeat.
style for Ethernet, can I apply the solution without hardware for PLE, just Ethernet interface?
Yeah, a very good question. And can you wait for 10 seconds? I will answer your question with the last slide. Okay? Speaking of adoption, part of the survey was also, are you going to considering private line emulation? And the answer was, yes, we're likely going to do that. So making it a standard, making it a product set that actually allows you to flexibly deploy it, I think will support that view there. There you go. Answering your question. So in summary, we talked about the private line emulation providing the bit transparency at the service layer, and circuit style segment routing providing the co-routed bidirectional end-to-end path protection, blah, 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 at the transport layer. So to your question, can I do Ethernet services in the shape of a private line without the dedicated hardware for PLE? The answer is yes. Now, you cannot be bit transparent, right? But if you, for example, use existing Ethernet pseudo-wire technology and combine it with circuit style, you are doing a frame-based connection, right? You can use the control protocol tunneling to be as transparent as possible. You can use Y731 for fault and OEM and whatnot. And underneath, you use circuit style to route the traffic, to manage the bandwidth, and have the end-to-end protection. So the answer is yes. And essentially, this is the whole purpose of this here. I'm not saying PLE will solve world hunger, but PLE is the answer. If you have cases where you need bit transparency or you need to carry something like fiber channel, you can do it. If you're fine with Ethernet and frames, go ahead, use Ethernet pseudo-wires. I'm perfectly fine with that. And depending on how you want the network behave, you can also use standard SR with ECMP. But if you want a more TDM-oriented behavior, circuit style segment routing would give you that. With that, thank you very much. I think we are 2 minutes over. Sorry about that, but we had some very good questions. I wanted to address them. Thank you very much for staying here. I hope it was interesting. And hope to see you in the future, and enjoy the rest of the show.